Hi everybody, welcome back. In the last video we talked about reflecting telescopes and refracting telescopes and started getting into why we are building bigger and more expensive telescopes. The first reason of which was a larger telescope has a much greater light gathering power and therefore you can peer deeper into the universe. There's also another very important reason that we're going to get into in this video, though after that we are also going to address such topics as adaptive optics and how we are able to get around the effects of atmospheric turbulence. So first of all, just a review about angles. So a degree is 3,600 arcseconds. In other words, a degree is a big area in the sky when you're talking about making precise telescopic observations. So astronomers usually prefer to use units of arcseconds for this. Now, there is a formula for the resolving power of an optical, or really just an observing instrument. And this formula does not need to be memorized, but part of it you need to remember. The first is that the shorter the wavelength of light, the smaller the resolving power. Second, the larger the aperture, that is, the diameter of the lens or the mirror, the smaller the resolving power. So resolving power is inversely proportional to diameter of lens or mirror and directly proportional to wavelength. Now, you want a small resolving power, because what this means, this theta min, this is the minimum angle that two objects would need to be apart in order for you to be able to recognize them as two separate objects. So if you plug in a certain wavelength of light at which you're observing and a certain diameter of telescope that you're using, if the angle between two objects in the sky is smaller than what you would get using this formula, then it is not possible to resolve those objects as two separate objects. In other words, they will just look blurred together. So a small number here is good, because if you get a small number, then that means, hey, if an object is separated by a small angle, you can actually resolve it if the number that you get is smaller than the angle by which the two objects are separated. So you want a small number here. So what does that mean? It means either observing at shorter wavelengths, though, as we'll discuss in the next video, there is a limit to that. And it also means observing using a larger diameter mirror or lens. And as we mentioned, the largest telescopes in the world are reflecting telescopes because of the fact that you can support those mirrors from behind and solve a lot of the other problems that you get when you're starting to deal with large lenses. So this is what we call the diffraction limit formula. And there is a problem here, though. While this is the limit that's imposed by the laws of physics and thus can't be violated, the true angle is usually a bit bigger because of atmospheric turbulence, and we're going to get to that soon. So, typical Kmart telescope will have a resolving power of about 2.5 arcseconds. So, if objects are closer together than that, then they will just look like one object. But the Mount Palomar 200-inch telescope, that 5-meter Hale telescope, that has a resolving power, at least according to the diffraction limit, of 0.025 arcseconds. So it can resolve objects that are much closer together. So if you look at a globular cluster with your average Kmart telescope, a lot of those stars will appear blended together. But with the 5-meter Hale telescope, they're going to appear as distinct stars. So there's that instrument. Now, what about this atmospheric turbulence limit? This is what we call seeing. Seeing is the minimum possible angular resolution of a star due to the effects of our atmosphere. Remember, stars are so far away that they should appear like points. So if they don't appear like points, that's because of either your limit of from the laws of physics, the diffraction limit, or atmospheric turbulence. So with that in mind, the best ever recorded seeing conditions at high altitude observatories are about 0.25 arcseconds. So that's 10 times the diffraction limitation of the Mount Palomar 200-inch telescope, and only 1/10 of that of the 2-inch Kmart telescope. So it's like if you can build a telescope, which you can just by buying the materials off of Amazon, that has a primary mirror with a diameter of 20 inches, then you have reached that. So it's like, you might wonder, why build a bigger telescope? Well, you can still perform observations much faster and look deeper into the universe with a much bigger telescope. And, as we're going to mention soon, there are other reasons around this. But yeah, this whole seeing thing, this is due to atmospheric turbulence. Seeing is the numerical quantification of the effect that we simply call twinkling. And one way around this is to get to the tops of the highest mountains where your seeing conditions are best. That's where, like on Mauna Kea, you can get angular resolution as good as about 0.25 arcseconds, which is why they have a whole lot of the observatories there. For example, the Keck Observatory is there. We already looked at that in the last video where we were comparing it with the Palomar telescope. Each of these telescopes is a 10-meter wide, has a 10-meter wide primary mirror. And yeah, that is snow on the top of Mauna Kea. They're also separated by 85 meters so that you can use a computer to perform interferometry techniques so that you can obtain a much better angular resolution for your image because of the fact that these are linked together over a larger distance. So that d in the denominator of that formula, that can also be the distance between instruments that are convolved, so to speak, so that you can use the phenomenon of optical interference to significantly improve the resolution of your image. But we won't have too much to say about the details of the physics of interferometry here because they don't really concern us. But yeah, you have lots of the big telescopes on top of Mauna Kea. The biggest telescope in the world, in fact, is also on the top of a mountain in the Canary Islands. It has one mirror with a diameter of 10.4 meters. And there's also the SALT telescope in South Africa, the South African Large Telescope, SALT. And that's 11 meters, but the whole mirror isn't 11 meters. So it's like 11 meters by 9 meters or something like that. So effectively, it's really more like a 9.5 meter mirror. But here's an image taken by the Gran Telescopio Canarias in the Canary Islands of a fading gamma ray burst. And this was a very important image at the time because before that, we didn't really have optical images of gamma ray bursts. There's also the VLT, which stands for Very Large Telescope. That's a system of 4 8.2 meter telescopes on a mountain in the Atacama Desert of Chile. So an image there, mirror coming up, and here they are together. So 4 8+ meter telescopes all linked together to give potentially significantly higher resolution images, like Crowd Nebula and GC 1232, etc. So here I have a few more telescope images for you, taken by some of the best ground-based observatories in the world. Here's one by the LBT. Now, how can we get past this atmospheric turbulence? There are actually a number of methods, one of the first of which was proposed by Crazy Fritz Zwicky. He was called Crazy Fritz by his colleagues because he was a very caustic person in terms of personality, and he also came up with a lot of really crazy ideas, including things like the possibility that neutron stars could be created by supernova explosions, or that the great majority of the matter in the universe is composed of dark matter. Yeah, really crazy ideas like that turned out to be correct. But yeah, his colleagues called him Crazy Fritz, and in turn he called his colleagues spherical bastards because, quote, they're bastards any way you look at them. But anyway, with adaptive optics, or at least for eliminating atmospheric turbulence, Fritz Zwicky's idea was to just aim a high-caliber rifle at a target and discharge a round to try to get all the air molecules aligned. It's hard to say whether this technique actually worked, but it is a very amusing method of trying to overcome atmospheric turbulence. But anyway, what adaptive optics is they use a system of a large number of pressure pads behind the telescope's mirror, kind of like active optics, but in this case, their pressures are slightly adjusted hundreds of times per second by a computer in order to cancel out the effects of the atmospheric turbulence. How does it do that? Well, if you're lucky, somewhere in your image is going to be a reasonably bright star. Well, that star should look like a point. So the computer keeps analyzing it and makes these adjustments until it looks like a point. And therefore adjusts the rest of the image accordingly so that it's much sharper. If you don't have a star there, then you can create an artificial star by firing a laser up such that it ionizes sodium atoms about 100 kilometers up in the atmosphere and use that as an artificial star. But it's a good technique for canceling out the effects of atmospheric turbulence. It's very successful. And there are other techniques as well. I'll mention speckle imaging soon and lucky imaging as well. But when you're performing imaging, we used to just look at it with our eyes. But then in the 19th century, we got photographic plates that could be used to collect light over a long period of time. And nowadays we have charge-coupled devices which are much more efficient than that. They're the basic elements that are used in digital cameras. But nowadays, charge-coupled devices for telescopes can be much more advanced than that. Now, in terms of canceling out the effects of atmospheric turbulence in your imaging, one way without adaptive optics is to use something called speckle imaging, where many images of the target are taken and you have the effects of atmospheric turbulence eliminated just by comparing features of the images and kind of moving them around and laying them on top of each other. This is perhaps somewhat similar to a technique called lucky imaging, where what you do is instead of taking one long time exposure, you take a whole bunch of short time exposures of the images, like very short time exposures, like fractions of a second. And in each case, generally there's going to be some blurring, but every once in a while, the effects of atmospheric turbulence just relax and the image is extremely clear. So you throw away all of the blurred images and you keep only the ones that are sharp. And using this technique, you can actually create some very good, scientifically valuable images just using amateur type of instruments. Now, in addition to imaging, which is basically taking pictures, there's also something called spectroscopy, which we've discussed before, where you use a spectrograph to break up the light into its components and analyze it to try to figure out the chemical composition, motion, other characteristics of your object. Then there's something called photometry, which is a measurement of an object's brightness or the brightness of objects in your image as a function of position. And then there's timing, which is a measure of how the objects or many objects' intensity or intensities change over time. In fact, the first extrasolar planets were detected using something related to timing called pulsar timing. So make sure to know these terms. They are very important. So now we've kind of rounded out our discussion of why we're building bigger and more expensive telescopes and how to get around the effects of atmospheric turbulence. But there's one method of getting around this that we haven't discussed, putting your telescope up in space. And that's what we'll start to discuss in the next video, which will round out our series of light and matter in telescopes. So I'll see you then, and thank you for watching.